Hello guys. So today we're going to discuss about the next topic, which is like it's about the linear independence and linear dependence. So let's see what is linear independence and what is linear dependence. And the example for the vectors, linear independent vectors and linear independence vector. Okay. So first, let us understand the actual meaning of it. So if I have the collection of the vectors, say v1, v2, v3 and say up to vp, they are in the vector space V. They are said to be linearly independent. Linearly independent if a vector equation says c1 v1 plus c2 v2 plus c3 v3 and so on up to say cp vp is equal to 0 has a trivial solution. So here this particular uh, you know the definition talks about you can see when it is talking about the trivial solution, it implies c1 equal to c2 equal to and so on cp is equal to 0, then this linear combination will become 0. So that's the understanding. So it's trying to say that whenever you have a linear combination of these vectors and it is equal to 0, either all these c1 c2 c3 are 0 when it is 0, and it's also 0 when not all c1 c2 are 0. So in this case we're talking about the trivial solution. That means all these constants c1 c2, I mean the scalar c1 c2 up to cp, all these weights are 0. That is the trivial solution. Similarly, the same linear combination we consider C1, V1, C2, V2 and so on up to say Cp, Vp, which is equal to 0. Still it is 0, but not all C1 to Cp are 0. So still this combination is 0. Then we call this vectors as linearly dependent vectors. Linearly dependent vectors. So basically linearly independent vectors means the linear combination of all the given vectors wherein the weights which we are talking about, they're all 0. Means it has a trivial solution. The system has a trivial solution. And when it has no trivial solution, then we call it as the linear dependent. So the linear, say for example, like some properties we can discuss under the same scenario. Like for example, say we have, if in the Rn a set containing a single vector, a set containing a single vector V is linearly independent. It is linearly independent if and only if V is not equal to 0. So if suppose there is a collection of vectors where only one vector is there, this is linearly independent only when this V1 vector should not be equal to 0. Now we're trying to understand the meaning of linear independence. So if there is a collection of vectors, if there is a only single vector which is not equal to 0, then it is always linearly independent. Now this is one note. Similarly, say for example, a set of two vectors is linearly dependent. Say I have a collection of two vectors, say v1, v2. They are linearly dependent. We're telling that they are linearly dependent. So when it is linearly dependent, it is possible when, if and only if v1 is scalar multiplication of v2. if one is the scalar multiple of other vector, then we say that it is linearly dependent. So it is one of, or you can say one is the multiple vector of another vector, or one is a multiple of other vector, then we say that they're linearly dependent. Then any vectors, any set of collection, any sets containing the zero vector, so then also they are linearly dependent. They are linearly dependent. It means, for example, I have say collection V1, V2 up to Vp, and in that I have a zero vector. In this collection, if I have a zero vector, then this whole collection will be linearly dependent. So these are some properties with respect to dependence and linearly independence. Okay, so now we have certain properties with respect to the linear independence. See, an indexed set. So in terms of the theorems, we have, say, an indexed set V1 to Vp. An indexed set V1 to Vp is like, say for example, of two or more vectors. Of two or more vectors with V1 not equal to 0 is linearly dependent. It is linearly dependent if and only if some Vj, say with j greater than 1, is a linear combination of the preceding vector. It is a preceding vector, say v1 to vj minus 1. So it is trying to say that you have a collection of vectors. If suppose you just choose any arbitrary some vector, say vk, then this vk vector, we say that this collection will be linearly dependent if some vk is the linear combination of its preceding vectors, say v1, v2 up to vk minus 1. If I'm able to write vk as a linear combination of this preceding vector, then we say that the whole collection, the collection which you're observing, this collection will be linearly dependent. So this is the actual meaning of this particular property or the theorem what is saying. Now, for example, what it is trying to say. Now, let me consider, say, P1 of t is equal to, say, 1. P2 of t is equal to, say, t. And I have P3 of t is equal to, say, 4 minus t. Okay. Then, you can observe, here I have three vectors, P1, P2, P3. If I write my P3 of t, can be written as, say, this is in terms of, the P3 can be written in terms of P1 and P2. If you observe, it is 4 times of P1 of t minus P2 of t. That is 4 into 1 minus t, which is equal to 4 minus t. So, P3 of t, you are able to write it as P1 and P2, means the P1, P2 are my preceding vectors of P3, where P3 can be written as the linear combination of P1 and P2. Thus, the combination P1, P2, P3 vectors, they are linearly dependent. So, this is one example for this particular property, which we have just stated. Okay. Now, similarly, let's see, we have another example. Let me take another example. Suppose we have like the collection of a set, say, sin t and cos t. These are linearly independent. They are linearly independent in the interval, say, 0 to 1. Because sin t and cos t, they are not multiple of any, neither sin t I can express in terms of cos or cos t in terms of sin. So therefore, this sin t and cos t are not multiple of one another. In the interval, the closed interval 0 and 1. So there is no scalar c such a way that we can write cos t as c into sin t. This is not possible. Hence, we say that this collection is not linearly dependent, but they are linearly independent for all t belongs to the closed interval 1, 0 and 1. Whereas, if I take the same one in this way, say sin t, if I consider the same example, sin t, comma cos t, and if I can take the sin 2t. If you see this one, here we can write, we know that sin 2t is nothing but 2 times of sin t into cos t. So here, this is true for all t. So here we can say that the third vector can be written as the linear combination of the other two vectors. Hence, we say that this collection is linearly dependent. So, these are some examples where we can say the linear dependency and linear independency. Okay, so now let's understand. We understood the linear dependence and linear independence. So now what we do is we'll see some vectors, whether the given vectors are linearly dependent or not. How do we check it? Suppose we are given with the vector, say v1 is equal to 3, 0, minus 6, and v2 is equal to say minus 4, 1, 7, and v3 is equal to minus 2, 1, 5. So determine whether these vectors are linearly independent or not. So how do we check it? So what I do is I'll just take the method of the row transformation, and we will check. See, there are many ways to find the linear independency. We can check the row. We do the row transformation, and once you do the row transformation, if every the column has a pivot position, every column has the pivot position, then we say that it is linearly independent. And once you do the row transformation, when you reduce it in the RREF form, then you conclude that if every column has a pivot position, then you say that it is linearly independent. Or not every vector is a linear combination of the other columns or the rows, then you can say it is a linearly independent. Then also, when you are expressing in terms of the invertible matrix theorem, once you do the, if it is, what do you say, if the matrix is invertible, then it is always those columns will be, corresponding columns will be linearly independent. So for the same example, you can solve it in a different ways. So now what I'm using is, I'm using the row transformation. So let's see. Now I'm going to take this in terms of, I'm writing in terms of the matrix format. So this one, you can observe carefully. So here we see that there are, this is our leading row, and these are the two rows which have to make 0. So convert it in terms of RREF form. So here, to do that, I'll now change R3 changes to R3 plus 2 times of R1. So now when I do this, I'll get here, this is 3 minus 4 minus 2, 0, 1, 1 as it is. This is 0. Then 7 minus 8. This will be again minus 1. And 5 minus 4. This is equal to 1. Okay. Now again what I do is, I want to make this element 0. So therefore, I'll just change R3 changes to R3 plus R2. So first you have to use R1 in order to make the lower element 0. Then start using the R2. Then we will use the R1. So now we can see that this is 3 minus 4 minus 2. This is 0, 1, 1. This is 0. Minus 1 plus 1 is 0. 1 plus 1 will be 2. Okay. So this we have got. Now I don't want this 2. Just remove this 2. R3 changes to 1 by 2 times of R3. This will be equal to 3 minus 4 minus 2. 0, 1, 1. So 0, 0, 1. Now we can use this element to make this element 0 and this element 0. That is, R1 changes to R1 plus 2 times of R3, and R2 changes to R2 minus R3. So simply it is 1. So therefore we can use this method. So this will be equal to 3. You can see minus 4, 0, it is minus 4 only. Minus 2 plus 2 will be 0. So 0, 1, this is 0. So this is 0, 0, 1. Okay. Now with the help of this element, we can make this element 0. So what we do is, I am taking this element, I am making this element 0. That is, R1 changes to R1 plus 4 times of R2. Okay. So once we do this, this will be now 3 minus 4 plus 4 will be 0. This is 0, 0, 1, 0, 0, 0, 1. Now from R3, you can change this element, that is R1 changes to 1 by 3 times of R1. So you'll be getting finally 1 0 0 0 1 0 0 0 1. So clearly now it is in the RREF form, where this is a leading element, below the leading elements are 0. The next leading element is this, where above and below elements are 0. The next leading element is this, where the above elements are 0. So now it is clearly in the RREF form, that is reduced row echelon form. So therefore every column has the pivot position. So therefore, by using the invertible matrix theorem, we can say that it is linearly independent, because no column is the scalar multiple of other column. So therefore, clearly the given vectors are linearly independent. So this is how we talk about linear independency. And when it comes to the the given vectors, whether they are linearly dependent or not, linearly independent or not, you need to check. So I just give some 3 cases where we can talk about, sometimes they are linearly independent, but they does not span, and, they are linearly dependent. All those things we will see in one example. So let me quote here. If in this case, say for example, you are considering 1 0 0 and you have 2 3 0. Here if you see carefully, here is a pivot position, here is a pivot position. So there are 2 columns which both have the pivot positions. Hence we can say that they are linearly independent. They are linearly independent. But if you see the spanning, if I take a linear combination of these 2 vectors, I don't have that one more vector which I'll get out of this combination. So that does not span. If you see the row wise, there is no the pivot positions. Hence they does not span R3, but they are linearly independent. So let me take this example where I have 1 0 0, I have 2 3 0, and I have 4 5 6. So here if you carefully see, we have a pivot position in all the 3 columns, because after doing the row transformation you will get definitely. So they are linearly independent. They are linearly independent. What about the spanning then? We can write this as the linear combination of this. So this one we can write 4 as, like, say 2 times of this plus 2, that is 4. Now we can write this one, say the one vector as a linear combination of other 2 vectors. If you write this one you can consider as C1 into 1 0 0 plus C2 into 2 3 0, then which is equal to, say, 4 5 6 if you consider, and or you can say plus C3 into, then whatever the solution you're getting, you'll be getting C1 is equal to C2 is equal to C3 is equal to, in such a way that you get a linear combination. So therefore it is having the spanning also. So in other words, when you do the row transformation, row also has a pivot positions. When you see the operations, you have columns also have a pivot positions. Therefore it is both linearly independent and it span R3. So then we have one more, that is example. Let me consider, if I take this one, say 1 0 0, then 2 3 0, then you have 4 5 6, then you have, say, 7 8 9. If I take this one, so this is actually spans. This spans R3. Okay, it has a spanning, but it is not linearly independent. You can see here there is these 3 columns are having the pivot position. What about this column? It has no pivot positions. Therefore, they are not linearly independent. They are not linearly independent, but they span R3. So we have seen the example where it is linearly independent but does not span. It is both linearly independent and span, but here in this case it span, but it is not linearly independent. So by these examples it is clear that sometimes it may be linearly independent plus spanning both. In some cases it may be linearly independent, but it may not span, and sometimes it may span, but they are not linearly independent. So therefore these combination of examples we may occur in future. So in the next session we will see the combination where both it is linearly independent and spanning. they're going to form the basis. That discussion we will do it in the next video. So till then, take care guys. See you in the next video.